Hi, thank you so much for having me at Parity Violation at Home. I'm going to talk about CP sources for electroweak baryogenesis. So, one of the triumphs of cosmology is that we can measure the baryon symmetry of the universe in completely different ways, and ultimately we get concordance between the two results. The two ways are to look at the deuterium abundance, the primordial deuterium abundance, which is very sensitive to the baryon symmetry of the universe. And we can also look at oscillations in the CMB, which vary depending on how much baryon symmetry in the universe. These two very different ways of measuring how much the difference between matter and antimatter are happen to agree within errors. Now, in some ways, this wouldn't be a mystery if we didn't have a period of rapid expansion known as an inflation. And the reason why inflation the reason why inflation is important is because ultimately inflation is a cosmic eraser. It just causes such a rapid expansion that it dilutes any initial conditions. So even if we had an initial asymmetry between matter and antimatter, which is order one, that would still not be enough because it would be completely wiped out by inflation. So we have to find a way to produce the asymmetry between matter and antimatter. So how do we do it? Well, any proposal which succeeds must satisfy three Sakharov conditions. You must have C and CP violation. You must violate baryon number, and you must have a departure from equilibrium. Or colloquial, you could think something about the laws of physics must treat matter different to antimatter. We must violate the conservation laws, since ultimately the antimatter asymmetry is stored in the baryon asymmetry. And we must see something which treats the future different to the past. So the standard model does have CP violation, but it doesn't appear to be enough. I know there's one interesting exception which came out recently, where you can use the standard model CP violation in a mesogenesis model. But generally speaking, it tends not to be enough. You do have baryon number violation at high temperature due to spherons, but you don't have any known departure from equilibrium. So you don't have the electroweak symmetry breaking cosmologically tends to be too smooth. So does QCD, the transition from quark gluon plasma to hadrons. So how is this achieved in electroweak baryogenesis? Well, the departure from equilibrium occurs during the epoch of electroweak symmetry breaking, which occurs if there's in electroweak baryogenesis inhomogeneously through bubble nucleation. What happens is, as the universe cools, you have a barrier between the true and false vacuum, which means that the universe cannot break electric symmetry smoothly, but needs to happen in small pockets of or bubbles of electric broken phase in a medium of symmetric phase. The baryon number non-conservation is the same as in the standard model. It happens through topological processes, electroweak spherons. So in electroweak baryogenesis, CP violation occurs through CP violating interactions with the bubble wall, which can create a charge asymmetry in front of the bubble wall. And that charge asymmetry could be a chiral asymmetry to begin with, or that chiral asymmetry, that charge asymmetry could be converted into a chiral asymmetry through transport. And then that chiral asymmetry, once you have a chiral asymmetry, since your spherons only act on your left-handed particles, having a chiral asymmetry will bias the spherons to produce more baryons and antibaryons, which will produce a net baryon asymmetry in front of the bubble wall. And as the bubble wall advances, that baryon asymmetry gets frozen in because spherons are suppressed inside the bubble, and you can no longer reduce the baryon asymmetry. So this is an elegant paradigm. It's quite a complicated paradigm, but it's quite compelling because it connects with something we expect to be quite likely to have happened in the early universe, at least quite possible. We certainly believe that it's likely that electric symmetry breaking happened in the early universe, and it's certainly possible that this occurred through a first order phase transition. So what is the health of this paradigm? Well, apparently, in some corners, people are worried about enough to have a paper called "Is Electroweak Baryogenesis Dead?" Now, of course, following the usual rule of headlines, the answer was no in this paper. But the fact that that question could be asked could reflect that some of the community is worried about whether electric dipole models are putting serious pressure on the most plausible models of electric baryogenesis. So this had a model which worked in the most pessimistic way of looking at electric baryogenesis and still gave a testable model in which electric baryogenesis was perfectly fine. However, it should be mentioned that even in the simplest models, it's actually really hard to say what the predictions of electroweak baryogenesis should be. So here's two particular ways of calculating the electroweak, the baryon asymmetry produced in electroweak baryogenesis, and they give you predictions which are 4 orders of magnitude apart. So this paradigm's been around for 30 years. So why is it so hard? Well, to be honest, we've been working on it, and we throw away all thermal widths and thermal broadening, a lot of the normal complications, but just really go back to first principles and derive things in a very, very rigorous way. And the thermal field theory calculation is very, very difficult. You end up being confronted with absolute walls of equations. So this is an example of a paper which I'm presenting on today, and it's 109 pages long, actually, and hopefully to be published any minute. But of course, paper this long, the editing takes quite a bit of time, but it's very, very difficult. So obviously it's impractical to expect people to do walls of thermal field theory equations every time they have a new model which they want to check. So what we want to do is we want to present a simple model independent form of your CPU violating sources that you can plug into a simple set of Boltzmann equations that mathematically can handle, so that people don't have to go through this over and over again. In fact, when I say over and over again, I believe that we're the first to actually go through it rigorously from first principles and derive an analytic source. So it's worth taking a small digression to say why predictions are so terrible. So we have this new result from Acme on the electric dipole moments, and we want to know, okay, is this what's the consequence for electric baryogenesis? We don't know. And the problem is, as you can imagine, looking at this complicated scenario of having a charge asymmetry in front of the bubble wall, expecting this charge asymmetry to fuse from the advancing bubble wall and seeds bias phalons, this is going to be a big mess. And ultimately, I think physics is always a big mess when you have different scales talking to each other. Ultimately, this is why quantum gravity is so hard, right? And here we do have different scales which matter. We have the scales of particle interactions, we have the scales when a particle feels the change in mass basis, and with the scale of bubble wall movement. So historically, what people have done is they've tried to simplify the scenario, and two ways is which are famous within the community. The first way is you just don't do quantum field theory, you just solve the Dirac equation with a spatially varying mass. This is sometimes called the semi-classical method. You end up with deriving a semi-classical force, but you don't get any resonant enhancement. The second way is what you do is you calculate diagrams, and you use the bubble. You treat it essentially as a perturbation, which you could just stick into vertices on these diagrams. You're basically sticking the bubble as a perturbation. And then you have to choose the degrees of freedom. So you make the reasoning that the degrees of freedom of the symmetric phase matter the most, because most of your baryon asymmetry is being produced just in front of the bubble wall, where your vebs are small and you're basically close to the symmetric phase. And then you can assume some local physics that that all your interactions are happening really, really close. And so this produces a resonantly enhanced source where you get like massive increase in your baryon asymmetry production when two masses are together, which can be very natural, because sometimes if your thermal mass dominates, you can have two masses. To be very, very careful. Have a careful calculation show that the traditional Web insertion resonantly enhanced source actually cancels, which is a bit confusing, because numerical studies did show qualitative features consistent with this approach, namely that you get this resonant enhancer. So can we derive it? Well, so there's a third method which people use, which was appeared in this uh, uh, numerical simulation which people did, which was this Kadanav-Baum source. And this is essentially something which people agree on because you're not introducing any crude approximations. Everything is nice from first principles. And ultimately, what you need is you need a good quantum number because what's happening is your degrees of freedom is changing, and that's ultimately what's making things so hard. So spin is conserved in both phases. So spin is a good quantum number. So we want to decompose our spin is decomposed into using this quantum number. So we want to decompose our propagators into spins, into helicities. And when we do that, we get a set of a couple of differential equations, which we can then expand. Second, we'd like to understand the Webb insertion approach. There seems to be nothing wrong with the Webb insertion approach. So why is it giving wrong answers? So we want to look for resonance which doesn't cancel. So if we derive everything rigorously using Kadanav-Baum and then do a Webb expansion, we do indeed find resonantly enhanced terms. And this is because you end up with terms which look like delta functions times propagators, where the propagator and the delta function will have different mass terms. So that's going to become ultimately a term which looks like 1 over m2 squared minus 1 over m1 squared. So then when we solve things, we actually solve things three ways because we actually solve things using WKB methods as well. All three ways agree and give us the exact same resonantly enhanced source, which is really, really interesting. So you end up, and what's interesting about this is a source which is fairly model independent. So if you have any source which will have two flavors, or alternatively one flavor, we have the one flavor source in there as well, but it agrees with, it's exactly the same as the semi-classical force, which is already in the literature. It's just a source which is just look at the terms here. You have M1, M2. There's nothing model dependent in here, and it's closed form. Yes, it took walls of equation to get here, but the actual ultimate source is fairly simple. So you can just plug it into your favorite model. However, even though we did find that all three methods gave this correct source, Webb insertion also gives us a bunch of extra crap, which is spurious. So you end up with this extra source, which is a vector source, and ultimately this vector source comes from having the wrong on-shell conditions, and there's no obvious way to improve it. The only reason you know it's wrong in the first place is because you're deriving other methods. And if you use the other methods to, in particular, the Kadanav-Baum through what's known as a constraint equation, you can use other methods to give you the proper on-shell conditions, which includes spatial dependent terms. Then when you plug that in, you can make them agree, but ultimately you don't know how to get that in any way using the Webb insertion. You're ultimately using the Kadanav-Baum, the full Kadanav-Baum anyway, so why not do that? So that's ultimately one drawback. So if you know the answer, you can use Webb insertion and you know which terms to throw away, but ultimately a priority is hard to see how to know which terms to throw away. But of course, maybe there's a way of doing that elegantly because Webb insertion can be very, very convenient. Okay, so a lot has been swept under the rug in this, in which so everything turns out to work out, but there was a lot of details which we had to work on. So there's, please see our paper, and please, especially if you're looking in Germany, there's a student which has been working very, very hard on this, who's interested in postdocs in Germany. So they deserve a lot of credit, and that's Baha Ilyas, who's been working on this for many years. Okay, so we want to test drive this with a simple model. So we're just going to have neutralinos. So it's a SUSY-like model. So we're not going to have charginos. We're not going to have stops. We're just going to ignore that just for convenience. But we are going to unignore the charginos because they become very inconvenient when considering electric dipole moments. So you can think of this, since charginos will contribute to the baryon symmetry, you can think of this kind of as a worst case scenario for the baryon symmetry, just ultimately because we want to examine the source and see how efficient it is. But it's a worst case scenario because we're underestimating the baryon symmetry, but we're including the full effects for electric dipole moment sources. So, yeah, ultimately, all the technology is there for SUSY. So all we have to do is get rid of all the stuff we don't want to bother calculating, like stops and stuff. Uh, and so what you can think of in these neutralinos is you don't have to really plug this into a proper SUSY model. You can just imagine this is a toy model with the same quantum numbers as SUSY, or maybe this is a SUSY model with heavy stops. Who cares? So anyway, we have neutralinos, and so this is what our source looks like. As we said, it's nice and model independent, and we can just plug it into the transport equations, which people know how to derive and use Fick's law to solve this. And we actually find something which is incredibly more efficient than the resonantly enhanced source, which doesn't exist. And the main reason for this is, yes, this resonantly enhanced source was very, very nice, but it also included and even though it's a lower order in derivatives, it included a cancellation where you have V1 prime times V2 minus V2 prime times V1. And secondly, it also was suppressed by the fact that you had a resonantly enhanced relaxation term, which is destroying your CP violation. And that actually doesn't exist in this term. So it might be the case once we include collision terms and all these other features that maybe you get some dampening. But one thing which surprised us is actually you get some parameter space, granted not much parameter space, but even in neutralinos, and this is we certainly could do a lot better than this if we're searching for models with smaller EDM signals. But in neutralinos, you have some parts of parameter space where you are consistent with your you have enough baryon asymmetry. You're below the EDM bounds, and you also are consistent with you're consistent with the approximations we had to use in order to get an analytic form. So electric baryogenesis is attractive. It's a low-scale solution to baryon asymmetry of the universe, that mystery. There's formidable uncertainties, but at least for fermions, we can derive a simple and well theoretically grounded recipe that mathematically a new student can handle and you can plug into your favorite model. So going forward, you want to include all your thermal widths and all these thermal collisions effects. And we also want to look at scalar sources.